Welcome everybody, and general overview, not quite right. I thought I'd talk about hybrid machine learning and motivated by means of a simple practical example. And that example has to do with physics. So let me first motivate why we are going to look into that particular example. We all know, I hope, that modern machine learning is revolutionizing the hard sciences. Last year, there was a Nobel Prize in chemistry, 2/3 of which went to Google DeepMind. Their system AlphaFold has completely disrupted chemical research, pharmaceutical research, genetic research. You couldn't do this on a top level these days without AlphaFold. Machine learning is of extreme interest to the hard sciences, to the natural sciences. And today we'll look into an example from physics. It's more like a lecture style. It's really trying to motivate what we're doing here. And what we're looking at is a didactic yet difficult problem. That sounds like a contradiction, but we'll see what I'm talking about. And it will sort of pop out that hybrid machine learning, which I'm not explaining yet, but at the very end, is the way of going for this. So today, first, ever so briefly, give some broader context. And we'll talk about modeling with differential equations as it's done by physicists. And then I'll point out the very difficult problem in this short presentation. And then we'll look at the hybrid machine learning solution and summarize what we saw. So let me set the stage. Nothing in the universe is ever in true stasis. Everything is constantly moving, rising, falling, growing, decaying, freezing, thawing. That may happen on very slow timescales, right? It might take millions of years for a mountain to decay, but it will. It may take hundreds of thousands of years for a mountain range to rise up, but it will. There's always motion in the universe we know of. And that means that everything that is physical in that universe we know of is in a state of perpetual change and subject to some kind of process. The ancient Greeks already knew this. This is a Pantarei from Heraclitus 500 before the Common Era. Now, the natural sciences, physics, chemistry, biology, study these kind of processes. And the modeling tool they employ, especially in physics, are differential equations. These modeling tools were so successful in physics, it's actually the unreasonable effectiveness of mathematics and sciences, that they also play a role in economics, more or less successfully there, because in general, the problem of solving differential equations, which describe how a system is changing over time, and the problem of putting them to use, which is what we're focusing on today, is excruciatingly difficult in general. Not today, but in general, excruciatingly difficult. And that has led to decades, ever since first electronic computers became available in the 1940s, decades of research on how to deal with these kind of mathematical objects on digital computers. That is basically what caused the whole field of numerical computing to exist. Lots of research on numerical differential equation solving. And nowadays, we are living in the day and age where machine learning can make a difference. And by the way, just 30 minutes ago, Patrick told me that one of our former colleagues, Bogdan Georgiev, I guess nobody in this room and in Dortmund will still know him, but he used to work here at the University of Bonn in the Machine Learning Rhein-Ruhr project, which was the predecessor for the Lamar Institute. 30 minutes ago, Patrick informed me that Bogdan has published a paper together with Terence Tao on basically this problem domain, because Bogdan is now at Google DeepMind and one of the developers of their AlphaEvolve system. So what we are going to look at today is where machine learning is really hot. Everybody's just talking about large language models, but the large language models haven't gotten a Nobel Prize yet. So let's look at modeling with differential equations. And I'll set up a super simple problem. Namely, let's consider the physical behavior of a ball that is being shot, like so or like so, whatever. Shot put athletes want to shoot that thing as far as possible. Basketball players want to shoot a ball towards a certain target. And to keep things simple, we will today model the behavior of the system in a two-dimensional plane. It may not be enough because in the real world there might be side winds moving the ball sideways or so, but for us it's good enough to assume that it is something that moves in the Euclidean plane. It has an x and a y coordinate. And at any time t, along this trajectory, such a ball will have a position, which physicists usually denote using the vector r at time t, which is just a two-dimensional thing here, x coordinate and y coordinate time t. It will have a velocity, that is the first temporal derivative of the position vector. And here I'm using a Leibniz notation, and this is Newton's notation. So if you see a letter with a dot on top of it, that means the first temporal derivative of that quantity. And it will have an acceleration, which is the second temporal derivative of the position vector, or the first temporal derivative of the velocity vector. And I will use two dots to indicate the second temporal derivative of the position vector. In order to fully characterize such a physical system that evolves in time, we need to determine initial conditions for this thing. And you may have wondered why I'm shooting the ball from the origin, 0.00. It's a choice I made. We could have chosen any point along the y-axis, but let's keep things simple, reduce the amount of variables we need, and fix the initial position of that ball at the origin 0, 0. And let's assume that it has an initial velocity at time t equals 0, which is a vector, like this vector v here, which has a length v and an angle theta by which that vector is rotated away from the x-axis. This magnitude v at this angle theta are model parameters. In what follows, I will largely assume them to be fixed up until later. For different choices of this number and this number, we get different behaviors. Let's have a look at those behaviors. What can we actually know about the dynamics or behavior of our ball? In other words, what does classical mechanics tell us about its movement? And as it turns out, quite a lot. This is really all 400, 300 years old physics. And what we know is that once the ball has been shot and is on its way, there will be two forces acting on it. One is gravity, that in our two-dimensional world just sort of pulls down along the y-axis. And the other one is drag. Think of that as air resistance. So the ball is moving in this direction and the air is sort of pushing against it. So that causes a force in the other direction than the ball is moving. And that means that Newton's law, which says that mass times acceleration is force, tells us that we have for the acceleration of the ball at time t, that it is equivalent to the sum of two forces, namely the gravitational force and the force executed by the drag. The mass m is yet another parameter of our setting, which I'll assume to be fixed. For instance, for a shot put ball, we can set it to 2.6 kilograms. And we need to talk about the drag. There's different ways for how we can model that. I'll go for the simplest one. That is called Stokes drag, where we say this force is but a linear scaling of the velocity of the ball at time t. There are other ways for how to model a drag. This is the simplest one that is physically reasonable. This here is the gravitational force. Both of them have a minus sign in front of it because gravity acts downwards, or drag acts in the other direction when the ball is moving. And once again, those are parameters near the surface of the Earth. This G is 9.81 meters per second squared. And for the drag executed by air, we can go for some small number here. Just to be clear, what we have done so far is making modeling assumptions, right? This is nothing new to people in machine learning. We have in machine learning typically are dealing with data and then need to decide for some model. Now in physics, we are dealing with certain systems and need to decide for how to make these systems as simple as possible so that we can talk about it, and we had modeling assumptions. And these modeling assumptions involved a couple of parameters. And if we choose them differently, for instance, keep the initial position fixed and the angle by which the ball is being shot, keep that fixed, keep the air drag fixed, then we may vary the velocity, the initial velocity, and if it is large, the ball will fly a long distance, and if it's smaller, then it won't. We can, for instance, vary the parameter of the angle at which it is being fired, and we can look at different drag coefficients K. These are different trajectories, but they look alike. I mean, they have slightly different shapes, but they all follow the same physical laws. So we should expect to see similar behavior under different initial conditions. And again, emphasizing, we did make some modeling assumptions. Modeling that in 2D is enough for us today, and assuming Stokes drag is enough for us today. May not be the case in general, so therefore, once again, George Box, all models are wrong, but some are useful. Now, what we just did when we wrote down the MA equals force equation is actually we set up two simultaneous differential equations. One involving the x-coordinate, or I should say first and second derivative of the x-coordinate of the ball, and one involving the first and second derivative of the y-coordinate of the ball. And given a system like that, we need to ask, okay, so we have a function x of t and a function y of t, but all we know about that function is a differential equation. So we need to look at these equations and actually determine what is x of t and y of t once again in that differential equation, which follows from Newton's second law. We only have second and first derivatives, but not the real deal. So we need to solve these differential equations, and this is where machine learning is extremely successful. However, the problem we are looking at today is so simple that we can do it using pen and paper. And I spare you the details. So who here in this room or in Dortmund is an expert on differential equation solving? I feared as much because during the quantum computing lectures, I was told that that is not necessarily taught in the math courses here. I actually studied physics and computer science, so I'm fairly well versed with differential equations. Very long story short, we have this system. We fix the boundary or initial conditions, and then going through some algebra, we find that this two-dimensional vector, x of t, y of t, is this is a two-dimensional function of time. The solution is given by this expression here. Right? No, I don't know. Just wanted to point out, like if we look at mathematical equations like that, this is easily coded in terms of NumPy. I just sort of like fix the parameters of our problem. The other one is in here. And I can define functions x of t, y of t, which really just are implementations of the equations we've seen on the previous slide. However, if we look at those trajectories, we do not plot the movement of the ball as a function of time. I mean, it is implicit here, but we see its x and y coordinate. So we still have some more work to do to get an equation y of x. Again, long story short, this is basically just algebra. We can do this. We can find this particular lengthy expression as the equation for how y changes with x. So if x is small, y goes up. If x is large, y goes down. And if it's captured expression there, and soon we'll meet the first derivative of this function here. The prime here is not a derivative with respect to time, but with respect to x. Right? So with that, I can plot these kind of things. I could simplify that, but it's not in the core focus here today. But once again, you can easily decode it. However, that was easy. So, I mean, it involved differential equations, but those were of a type where we really don't need machine learning to tackle them. Usually, I don't know, think about fluid of motion, stuff like that. Navier-Stokes equations as being solved by DeepMind these days. It's excruciatingly difficult. This was easy, but there is a difficult problem hidden underneath the surface. Think of this, in practice, nobody actually cares about the particular shape of the trajectory. The question is, where will the ball land? And what x-coordinate will the y-coordinate if it starts at 0 be 0 again? Right? So what we want to have in practice is, if I give you the initial velocity, magnitude of the velocity and the angle under which the ball is being shot, then we want to have a function d of v and theta, which returns d, the distance the ball will be flying under that choice of v and theta. And that means, like we know the function y of x, we also know at x equals 0, this will be 0, and then there has to be another x value for which this thing is 0. That's the non-trivial root of this equation. That thing is non-trivial because I encourage you to look at this equation and give me a closed form expression for given v and theta for which x will y be 0. You will not find a closed form mathematical expression. It does not exist. That means that we are now dealing with an optimization problem, something that is much, much closer to machine learning. And I'm writing it like this. The function d of v and theta we are after actually returns the arcmin dx, which is greater than 0, for which this here is as small as possible. And this is an absolute value. And since that thing will be smallest for the phi value of 0, that actually does what we want. It looks a bit strange, but this is the problem, the function we are after if we want to know how long the ball, where the ball will land. Even worse, most practitioners are not really interested in how far the ball will fly, but they know it should land over here, for instance, the basketball player, and therefore have to ask the question, how do I have to choose theta and v in order for the ball to land there? Here, we really hit a problem because this P of d, the parameters of the given distance we want to achieve, this cannot be a function. Because look at that. Here, the ball has landed there, and there's already sort of at least two choices for the velocity and the angle under which the ball will land there. And a function can't return two values or two vectors of parameters. So this is not even a function. And that then leads to the topic of today. In order to compute this distance function, which is a function, and to estimate these optimal parameters, angle and initial speed, we must work either with numerical differential equation solving optimization techniques or nowadays with machine learning models. Ever so briefly, because I'll need it to set up the machine learning model, we'll look at how numerical techniques would approach this thing, especially problem of finding the non-trivial root of the distance function. You can just use Newton's method. We guess a solution and then perform a couple of iterations in which we incrementally update our solution. And it is Newton's method because it involves the function y at our current estimate xk and its derivative y prime of xk, and that is why I've wrote down the derivative sometime earlier. Now, this is easily coded, again with Python NumPy, can wrap that in a function distance, and from now on I'll assume that this function distance is given. With that function distance, we can then sample this analytically impossible function d of v and theta. Again, there is no closed form. This is just argmin over all the x greater than 0, for which the absolute value of y of x given v and theta is small. That is the function, and there is no closed form solution. That's what I mean by analytically impossible. But we can choose a couple of v values and theta values, and then use our function distance, iterate over the v and t values, to compute the corresponding distance value. And if we then pretty plot the result of this array of distance values for the range of initial velocities, I considered from 5 to 85, and the range of initial angles, again, consider 5 to 85, we get something like this. Right, and that is a sampled version of this analytically impossible function. Let me emphasize that this picture looks super continuous. It looks like as if the distance varies continuously. But that is not the case because we sampled it on a grid. I'll get back to that in a second. And once we have this estimates of our function, one would think that we can use it to get to this function we really want. Like if I give you a distance, how do I have to choose the angle and the velocity? That distance here is quite visible. Let's say we want to hit a distance of 150 meters. I can just sort of subtract that from the distance for v and theta. And if we look at the original function, d of v and theta, and then of the subtracted version here, we see that there is a lot of values for which this is very small, or 0. And then there's lots of values for which this rises again, and lots of values for which this rises again. So it's a very sort of like complicated function, definitely not a function you see in math classes. All right? And it corroborates that the optimal choice of parameters for a given distance is not a function, but because there's lots of values, v and theta, we can choose to achieve this distance. So what we see here, once again, it's like something that looks like this, grows towards this side, then declines in a funny shape, and then grows again. And I've already said it, like what we are dealing with is function values on a discrete grid. This is the characteristic of numerical methods, that at their very heart, there is some discretization. And it then means why we can't do gradient descent. I mean, you know, if I want to shoot the ball 150 meters, I guess some parameters and then just follow the gradient until I end up at a parameter value pair for which we hit 150 meters. We can't do this because this is not a continuous function. It does not have a gradient. We can numerically approximate that. We can use interpolation and the like to do this. And this is where this decades of research went into. And nowadays, we don't have to worry about this anymore. This is just to motivate why grid methods are not ideal we are only dealing with two parameters, velocity and theta, but I could have introduced the height from which to shoot the ball, right? And then it would have been 3 parameters. And you can see that the sizes of grids we would need to model that as precisely as possible, they grow exponentially, right? This quickly grows out of bounds. And this is where machine learning is coming into play. This is why more and more people in the MINT fields are so excited about what modern machine learning has to offer. And then finally, that leads us to hybrid machine learning. So what we can do is, instead of considering a grid of 10,000 points, let's just randomly sample 1,000 points in this parameter range here. And that looks like that. This is really the 1,000 sample points I got. And for each of these sample points of the two-dimensional vector v and theta, I can compute the corresponding distance of the ball going to fly. We have that function distance. And I can therefore collect all the pairs of v's and theta values in a 2 by 10,000, 10,000 by 2 matrix, and can collect all the distance values that correspond to those particular choices in a target vector, and now have training data to train or learn a model function d of v and theta. Again, this thing is analytically impossible, but I can now use machine learning to get a model for that thing. Right? And here is how I did it for today's presentation. I just set up a neural network, which takes as input v and theta, and as output produces d. For reasons that will become clear soon, I'll call this network a decoder. And here are my modeling choices for layers, so many neurons per layer. I consider the least squares loss as the optimization objective, then naive gradient descent. Why? Nobody knows. It worked well. Right? This is machine learning. This is a craft rather than a science. Nobody knows. This was a great compromise between the time it took to train the neural network and the result it produced. Could have spent more time on making it smaller. I didn't. And so importantly, once I have trained the decoder, I can test it. And this is the function we got, or the picture of the function we got from sampling from the 1,000 by 1,000 grid, 100 by 100. And this is what the neural network learned. And I don't know if you see any difference. I hardly see any on my screen. Didn't evaluate it numerically, but this is basically the same thing. Right? This was learned from 1,000 random points here, and this really just pictures the values at these discrete grid points. Same thing, we now have this sampled function and this neural network model, DNet, and this is a continuous function. As I can, at least to the numerical precision afforded by floating point numbers, vary these things here, and this thing will always spit out a distance value. So, long story short, we could use this neural network and use modern machine learning libraries with autograd capabilities to perform gradient descent on the function it learned. But we can also try something more ambitious. And that is to train this encoder-decoder network. Once again, this is not very reasonable, because what I'm trying to learn here is you give me a parameter d for the distance you aim at, and then a neural network will compute the corresponding initial velocity and initial angle. And this is an autoencoder model in a sense, because if d comes in, d is supposed to come out. Right? And together, these two neural networks, therefore, are supposed to learn the identity function. If d comes in, D is supposed to come out. The crucial point is that I'm forcing the encoder to produce these two numbers, which the decoder can then use to recreate the distance we are aiming at. And these are my choices for how to do this. Nobody cares. Here's more about my choices. Nobody cares. I can run this. For instance, set the target distance to 150 meters, and then run the whole model here to get those results. If we look at these numbers, then we realize that this thing has a preference for rather small angles. That's what the network learned. But if I use these two initial parameters, we really get 150 meters. So very importantly, I said it at the beginning that this here is not a function, right? And yet, neural networks can learn to produce reasonable output on reasonable input. This is a function. It takes these two numbers and produces another number. In reality, there is no such function, but this neural network has learned at least one function that does that. And again, this function has learned a preference for small initial angles, but high initial velocities. Works. But why so convoluted? I mean, why do we train the identity function on given distances as input? It's supposed to produce given distances as output. Why? I mean, if I can sample these and compute it, it can train a network directly, right? This takes in a distance value and spits out a pair of velocity and angle. Why did I choose to go for an encoder-decoder architecture here? And pre-trained the decoder. Any idea? It would be super, super difficult if we were to take this kind of training data with this is the input, and this is supposed to be the output. Super difficult to come up with a reasonable loss function for training the neural network. And that has to do with the fact that velocities and angles are different beasts. They're physical in the sense of in nature, their physical meaning is completely different. The one is a speed and the other is an angle. And if we would just say, well, the loss should be, we feed in a distance, it spits out a prediction, and that prediction is supposed to be as close to the true target values we have. And of course, we can say, let's go for these squares here, but that does not make sense. Because this is a vector of two numbers that have nothing in common. And this one here can be much larger than the other. The other is basically, doesn't make sense to consider values larger than 90 degrees because then it fires in a different direction, right? But this here can be, I don't know, 10,000 meters per second. And this here can only go up to 90, or it can go the whole circle. But this is a physically unreasonable vector. There is no reason from the point of view of nature to work with that. And because this is physically unreasonable, the whole thing is physically unreasonable. It will work. It will definitely, produce you something, but that then would be a black box neural network, which solves the problem we are after, but we could not trace back why or how reliably it solves the problem we are after. this is not physically adequate. However, from here to here, this is physically adequate. I can pre-train the decoder with a pair of velocity and angle, and I want to get a distance. I have in my training data inputs and outputs, and I have a prediction of that network. The prediction is a distance, the training target is a distance. There it makes sense to work with least squares loss to keep things simple. But once I have trained this here, and then in a second step, put this below and train that, then again, the input is a distance and the target is a distance, and I can use least squares because comparing two distance values makes sense. So in that sense, this encoder, which takes distances, maps it to velocities and thetas, which then are mapped back to distances. Here, we do not have to worry about how to set up the loss function for our training process. And what we've seen there is an example for hybrid machine learning. Because this model architecture, I mean, I made it up like 4 layers here, so nobody cares. The important thing is I forced a learning problem that had to go through a physically reasonable bottleneck. And I first trained this. From here to there, I can be sure that that makes sense. Right? It's not a function, but it can learn a function. And once we have that, we can put this in front, force this through this physically interpretable bottleneck of these two neurons, from where it then just predicts the distance again. So this here learns to, given a distance d, encode v and theta such that the pre-trained decoder reproduces the distance. Hybrid machine learning makes use of knowledge. It learns structured representations, either of models or of empirical data. And hybrid machine learning models either incorporate structure into the representation of the data or into the model design. And what we've seen here was an example for model design. What I did here in very fancy terms is I leveraged inductive biases. This is really, I hate this term, but it's very popular among machine learners because it sounds so scientific, right? It really just says, don't learn a black box, but learn one black box with reasonable input-output behavior, and then put another one below that, where that below should produce an output which is reasonable with respect to what was learned previously. So like by considering this architecture, I'm forcing this thing here. I have an inductive bias towards interpretable values of velocity and angle. And do not underestimate the importance of this kind of use of information. Another word for that would be inferred machine learning. I really set up a neural network model that adheres to physical background knowledge. And this is, for machine learners, we couldn't care less. But if I was a physicist, then a black box is meaningless to me. And it solves my problem, but it doesn't tell me anything about the physics. But bringing together this mathematical/physical knowledge with the data we use here from simulations, we can get machine learning models that are interpretable and that make sense to the practitioners in physics. Right? So this is super important in the real world. The predictions produced by a model must be reliable and explainable. And it turns out that for large language models, at this point in time, this is not the case. Just go see Professor Bayrat, he can tell you about this. So what we've seen today is there are difficult problems out there. The one we looked at today was not solving a differential equation, which is super really sensitive problem for machine learning. It had to do with getting certain solutions coming out of the solution of the differential equation, namely this inverse kinematic problem. I want to achieve a distance d. How do I have to choose the parameters of my system? And addressing that problem, we've come across the idea and benefits of the paradigm of hybrid machine learning, which once again uses knowledge and data to force models towards more reasonable predictions. That is my presentation. Thank you.